Hello friends, in this video we'll be continuing our F equals MA 2019 A problem series, and we'll be covering the problems numbers 7 to 9. Let us start with number 7. An object of mass m is attached to the end of a massless rod of length L. The other end of the rod is attached to a frictionless pivot. The object is raised so that its height is 0.8 L above the pivot, as shown in the figure. After the object is released from rest, what is the tension in the rod when it is horizontal? So here we could easily use conservation of energy. Essentially, we know that the delta H is equal to 0.8 L. And we know the object's mass is m, which means initially the object has an energy of mg 0.8 L. Now we just need to convert this to kinetic energy, which is equal to 1/2 mv squared. Then from here we just need to find the tension, and the tension can easily be found using centripetal force. So we just do tension equals mv squared over r, or over L, because L is the radius. So now we can just solve for v in terms of these variables, and we'll have the m's cancel here and get 2gl 2g 0.8 L equals v squared. So then we just plug that in to the equation for centripetal force. You get m 2g 0.8 L over L. So our L cancels out, and now we're just left with 2 times 0.8, which is going to be 1.6, and then mg. And so this is our answer. It's just going to be B, 1.6 mg. Yeah. Now let's move on to our next problem. Moving on, number 8. The mass and radius of Earth are m and r. If an object starting at a distance of r from the Earth's surface is moving at a velocity v0 equals 2gm over 3r tangentially, what is its trajectory? Okay, so for this, we should probably calculate the escape velocity and the velocity for perfect circular motion. We can calculate the circular motion by using force, I guess. We can have gm m over r squared equals m v squared over r. And from this we get v equals square root, small m cancels, so square root gm over r. Yeah, this is our circular velocity. Now for our escape velocity, we could just use energy. So we have gm m over r. And remember this right here, gm m over r, the reason why it's really similar to gm m over r squared is because gm m over r squared is basically force, right? And force times distance equals energy. So we're just multiplying by r again. That's why the r squared is gone and is replaced by r by itself. Now this equals our centripetal, or not centripetal force, our kinetic energy, which is just going to be 1/2 mv squared. This is going to result in 2gm over r, and the whole thing under the square root. And this is escape velocity. Okay, so like now we can look at our like velocity that's given. v0 equals root 2gm over 3r. So like notice how this is like less than our circular velocity. So this means like it's probably gonna be like elliptical or something. And then let's see, 2gm over r is greater. Yeah, and that's our escape velocity. So it's like, yeah, nowhere nearer to our escape velocity. So like, we have the Earth now. So this is not a hyperbola. It's not going to be a circle because remember, this circular does not match this VO. It cannot be a straight line. So like we're stuck with like choices C and D. So like let's assume that it's an ellipse where the maximum distance from the Earth's surface is r. Well, if that's so, then essentially we have like our thing starting here and then going with v0, and it might go across and then like slowly come back. But then if you compare it to like the Earth being stationary, the Earth being here, and the minimum distance being r, this being r, then like even if the speed is like quite high, the VO, by the time it gets to like this peak of motion, it'll probably like come back around and it won't like lose orbit, so it won't like escape. Yeah, so that's why like C is correct. Now we can move on to our last problem. A wheel of radius r is rolling without slipping with angular velocity omega. For a point A on the wheel at an angle theta with respect to the vertical shown in the figure, what is the magnitude of its velocity with respect to the ground? So here's our wheel. Let's draw it. Okay, fine. That was a bad picture. This is better. Okay, so you have like A here, and then like theta, like right here. No, it's spinning at omega. Okay, so like we need to find the magnitude of velocity. So that means we need to find the x component. And let's assume that it's like spinning this way. Right, so that's like clockwise, if you're looking at it from the side. So then like that means A is gonna move like in a negative x direction and down as it like approaches like this point. And in order to find like our horizontal velocity vector of A, I guess we could just like, yeah, we could just use like similar triangles here. We know that A is tangentially, A's velocity is going to be tangential like this way, right? We want to find its horizontal velocity. So like we just need to find essentially like this line right here. And we already know that like the tangential velocity of A is just going to be A tangential. So velocity of A tangential is going to be equal to WR, or not W, omega R. Yeah. So that's the tangential velocity. And since like this right here is like theta, and we want to find the horizontal, we're gonna find like Vx or VA tangential x equals cosine, yeah, so cos theta times omega r. Okay, and now essentially we could like find the total horizontal velocity of this point A, because like by simply just adding our velocity of center of mass, and VCOM is just gonna be omega r. So what we have here is like Vx equals omega r minus omega r cos theta. Okay, good. Now for like the vertical, the Vy, we can just do the same thing. You're trying to find this, that's just gonna be like sine. So Vy is just gonna be like sine theta times omega r. Okay, yeah, so now like all we had to do is just find the magnitude. So let's scroll down a bit. So we have like the absolute value of V is going to be equal to the square root of like Vx squared, which is going to be plus Vy squared. So okay, now we can like expand. That's gonna be minus my god, this is gonna take forever. Okay, then plus omega r squared sine squared theta. Yeah. Okay, and now like we can see like some common things over here. We just like take off like WR squared out of everything, or omega r squared out of everything, and that gives us omega r square root 1 minus 2 cos theta plus cos squared theta plus sine squared theta. Yeah. And yay, look what we have here. We can just use our like Pythagorean trigonometric identities, and this is just gonna be 1. Okay, so like now for our final steps, we just have to add this 1 to the 1 at the front. That's gonna do 2 minus 2 cos theta. Oh yeah, and of course there's still the omega r at the front. Okay, so like right here we see 2 minus 2 cos theta. Let's take the 2 out. You have 1 minus 1 cos theta. And since this whole thing is under the square root, we can kind of see that this kind of resembles like the half angle identity for sine. And yes, sine theta over 2 is equal to square root of 1 minus cos theta over 2. Okay, so like that just means we just had to somehow get this in the form of like over 2. And we could just do that by like, I guess, multiplying and dividing by square root 2. Yes, okay. So we're gonna have WR or omega R equals 2 1 minus cos theta times 2 and divided by 2. And since all these are under the square root, we're effectively like multiplying by root 2 and then dividing by root 2. Like in the end, this just gives us 2 omega R. And under this square root, we have 1 minus cos theta over 2. And that just like turns into, since we use the identity, that just turns into 2 omega R sine theta over 2. Yes. Okay, yeah, look, we have 2 omega R sine theta over 2 as choice E. And so, yeah, E is correct. Okay guys, if you enjoyed this video and would like to see more, please dunk on that like button like I'm about to on this stupid tank.